This is the introductory video for the uniform circular motion experiment for the Physics 1101-1120 labs. This is our basic apparatus. We've got a box and there's a rotational apparatus sitting on top of the box, and then we have a platter here that spins. And mounted on top of the platter we've got this track. We're going to have a little car that sits on the track later. I'll show you that in a moment. But for now, just notice that this bit spins. There is right here a little arm that has a motor, and that's going to cause the platter to spin at a constant speed. So I've got the control box down here. Mounted over here, where you might have a little trouble seeing it, we've got a photo gate. And the reason why that's there is that I have a little cardboard flag taped to the top of the platter, and that flag is going to go through the photo gate on every single revolution. And using a computer program, that will allow us to time one complete revolution. So that time for one complete spin is called the period of rotation. That's one of the things you're going to need to get today. So let me now show you what it looks like when this thing is spinning. So first of all, I've got my control box for this guy not plugged in right now, and that's for a good reason. There's no on-off switch for this. As soon as I plug it in, he's turned on. So to begin with, I make sure that the speed knob is turned right down to minimum, and then I plug it in. So that makes sure that nothing surprising happens. So now it's plugged in, it's ready to go, and I can turn up the speed knob, and it causes the apparatus to start spinning at a constant speed. So I'll turn this off now and tell you about some other things. So before you start taking data, you want to first get the apparatus ready to use. So to begin with, you want to make sure that this box is nice and stable. So you can press on this and just see if it rocks. And this one is right now. So down here at the bottom there's two little screws, and you can adjust those to fit snugly against the table. And if you do that, then you should find that the box no longer rocks. So get this box nice and stable. The next thing you want to do is level this apparatus. So you've got a spirit level on your desk, and you put this on the base of the apparatus. So not the spinning part, but the rectangular base. And you may need to climb up on top of the desk to do this, but you want to look straight down at the top of that spirit level and make sure that the bubble is centered inside the circle. If it's not, then the bottoms of these legs have little screws on them, and you can use that to adjust the leveling of the base. So do that as accurately as you can. Climb up on the desk if you need to, look straight down at the top of the spirit level, and adjust the bottoms of these legs until the bubble is centered in the circle. So once you've done that, then your apparatus is leveled, and you're ready to continue on. Now, as I said, you've got this little car, and it's going to be sitting on top of the track. So if I unravel this, I've got a string attached to this guy. I'm going to put the car on this end of the track that has a post to keep it from falling off. There's also tracks in there that it rests on. And this string has to thread down through the center hole in the apparatus. Now, before you do that, you need to weigh this guy. So weigh him first and then put him on here. And to help you actually thread this thread through the hole in the center, you've got this plastic doohickey on your desk, or possibly a piece of wire with a hook beside it. And you're going to use this basically as a needle to thread it down through the center of the hole. So you can hook the thread on top of the wire and then thread that down through the hole in the center of the apparatus. And it should be long enough that you can then pull it down from below and get that thread hanging through the center hole and down. And there is a little tiny pulley on top of here, and you want to make sure that the string goes through the groove in the top of this pulley. So here's a close-up of the top of the track. There's these two little grooves, and the wheels of the trolley are going to run in those grooves, so back and forth like that. There is also this pin on the end of the track, which keeps the trolley from falling off and hitting your partner in the nose. The other side of the track does not have any grooves, does not have any pin. Notice when I pull the trolley way back that this little pulley in the center has a little groove in it. The string has to go over that groove and then down through the hole in the center of the apparatus. So make sure that it threads over the groove. Over here, you see the little flag. That's going to trigger the photo gate every single time it goes by. Now, the perfect length for that string to be is that when the cart is in the center of the track, down here we're going to be hanging a little mass hanger off the end of the string, and you want that mass hanger to just barely be touching the bottom base here. So you're going to need to put a loop in your thread, and to do that you should use a small piece of masking tape. Please don't tie knots in the string. It makes it really difficult for us. So just to demonstrate, I've got my cart in the center of the track, I've got my string adjusted, and then I fold it here and add a small piece of tape to make a loop. And that way there's no knots in the string for the technician to have to untie later, and I've got my string set to the correct length. You also are going to need the mass of this mass hanger down here, so take this off and weigh it, and after you're done, then you can then hook it onto the string again. So let me now show you what it all looks like when this is in action. So what we're going to do is we're going to start the apparatus spinning, and we're going to be lifting up this mass hanger such that the trolley is going to be in the center of the track somewhere and not moving relative to the track. So it will still be moving in a circle, but relative to the track it'll just be sitting in one location. The mass hanger down here is not going to be moving up or down. So again, the trolley will be somewhere in the middle of the track, not sitting at the center, not sitting against the post at the end, but just somewhere in the middle, and this guy will just be dangling in empty space. He'll be spinning, but he won't be moving up or down, and the trolley won't be moving back or forth. That's what we're looking for. And so when you get that state of affairs, then you take your data. Now the speed that you set this guy spinning to is going to determine what the period of rotation is. And for every period of rotation, there's one particular radius that we expect to get, theoretically. That means that this experiment's not terribly reproducible. In other words, if you're halfway through your data taking and something goes flaky and the trolley flies to the center or flies off to the end of the track, you would actually have to start from scratch because you can't be sure that you'll get the same speed a second time around, which means you won't get the same radius. So you have to take your data all at once. There's only two things you need to take, however. One of them is the period of rotation, which you'll get using that computer program I'll show you in a moment, and the radius of rotation, so the distance from the center of the trolley to the center of the hole in the middle. I'll talk more about how to get that radius r in a moment. So I'm going to show you what this all looks like. And the lab manual, what it tells you to do is to start with the trolley in the center of the track, start things spinning, and then you lift the mass hanger until you find that radius where you can just let go of the mass hanger and the trolley stays in the same location relative to the track and the mass hanger is just dangling in space, not moving up or down. I actually find that method doesn't work as well as doing the following, and that is you start the trolley out at the end of the track and you support this guy so that the trolley doesn't really move, and then you turn on the motor. So right now, the trolley is off at the end of the track. We don't want that. We want it sitting in the middle of the track somewhere, and we have to find that radius. So, like I said, this is what works slightly better than what the manual describes. The manual says start with the trolley in the middle. I say start with it out here at the end, and then rather than lifting this mass hanger, we're going to pull it down to find that radius of rotation. So now, I pull this mass hanger down, and it'll be a little touchy to find this spot. But there should be one location where you can just let go of the mass hanger and the trolley is going to stay stationary. So relative to the track, my trolley's not moving anywhere and this guy is spinning but he's not moving up or down. So this is actually an unstable equilibrium, which means that if there was no friction in the system, we'd have a hard time getting the trolley to actually stay at this location. But because we do have a little bit of friction, it will actually stay put, and unfortunately that sort of thing can happen. Things will just go out of equilibrium and the trolley will either fly off to the end or go back into the center. So if that happens, it's okay, just go ahead and find your radius of rotation again. And because that sort of thing does tend to happen, what I recommend you do is once you find this radius where it's quasi-stable, just wait a minute before you start taking data to make sure that things aren't going to go out of whack. So I would leave this guy rotating for a little while to make sure that things are going to stay stable, and they're not. And it seems a little bit happier here. This radius is actually pretty far out there, but it's not resting against the post at the end of the track. So this would be valid. I could take data off of this. If it is sitting on the end of the track, then you need to increase your speed in order to get a smaller radius. So there's two quantities that we need to measure. One of them is the period of rotation, so one complete spin, and the second is the radius of rotation. So from the center of the trolley, the center of that post, over to the hole in the middle of the apparatus. Like I mentioned, there is this pulley at the top. You don't want to use the center of the pulley, you want to use the center of the hole. So to get the period of rotation, you're going to use a computer program. The only thing that's going to be tricky about this is we need to get the radius of rotation, and that's really hard to do when everything is moving. So this is something we leave open-ended on purpose. You're expected to come up with a way to measure the radius of rotation. You may not write on our equipment, but you can stick tape on the side of the equipment and write on that. So some people will actually make their own little ruler on there and try and measure it. Some people will actually try and photograph it if they have a camera on their phone. Other people don't try to measure it while it's moving at all. They might, for example, brace their hand on the bottom of this apparatus, pinch the string, turn off the motor, and then stretch the string out and measure the location of the trolley originally. So there's a variety of ways that you can measure that radius. Whatever method you choose, make sure that you describe it well in your lab notebook. So that's worth marks. Things to think about when you're doing this is that you should have some physical uncertainty due to estimating where the center of the hole is, some physical uncertainty due to the size of the spindle in the middle, and some physical uncertainty maybe due to the technique you're using to measure the radius of rotation. So think carefully about it, and whatever you choose to do, write it up well in your notebook. So as usual, go into the PhotoGate VIs folder, and this week we're going to be using a program called Period Timer. So we're timing the period of rotation of the apparatus. So as usual, you just click the one single white arrow at the top. This little guy will go green, and the program will automatically start and stop taking data for you. So right now it is filling in data, and when it gets all 10 of them, it's going to give me an average period, and that's what I would write down, and the uncertainty you can use is 1% for the PhotoGate. So now I'm going to talk a little bit about the theory that governs this experiment. So to do that, I'm first going to get this guy moving again, but I'm going to use a faster speed just so that you can see the trolley sitting at a different location. So again, I move my trolley right to the end of the track, support the mass hanger so that the trolley does not move around, and then I turn up the speed on my motor. And I've gone to a faster speed now. I'm roughly at the second E in the word speed. And so now I grab the mass hanger and I pull it down to find that radius where the trolley is going to be happy just sitting still relative to the track. And that's roughly there. And as you can see, the trolley's sitting a lot closer to the center this time. And that's just because I've got the speed of this turned up. So, the theory. Newton's first law says that a body in motion tends to move in a straight line unless acted on by a force. We've got a body that's moving in a circle, not a straight line. So that means there must be a force acting on it. Otherwise it would be moving in a straight line, not a circle. So, where's that force coming from? It's just the weight of the mass hanger, which pulls down and therefore pulls the trolley towards the center of rotation. So that weight is our force. So the purpose of this experiment is we're going to calculate the force we expect the trolley to feel based on its radius and its period of rotation, and we're going to compare it to mg, the mass hanger's weight, to see whether those two numbers agree within their limits of uncertainty. Just be careful that you don't mix up the two m values. So the mass of the trolley and the mass of the mass hanger are slightly different. Just be careful you don't interchange them in your calculations. So this is the theoretical force that the trolley feels. So the manual explains how we got this, but it's all based on an understanding of the rotational motion. So we calculate this force based on the mass of the trolley, its radius of rotation on the track, and t, which is the period of rotation, so the time for one complete spin. As I said before, the point of the experiment is we're going to compare this quantity, to mg, where m is the mass of the hanging mass, and we'll see whether or not those values agree within the limits of uncertainty. Now one thing I'll note here is that mg doesn't change, right? So the mass of the hanger doesn't change, gravity doesn't change. This is a constant over here. But over here we've got things that can change. So for example, this period of rotation will get smaller if I speed up the platter. So if it's spinning faster than the time for one spin gets smaller. That means that the radius of rotation also has to get smaller in compensation. So radius is in the numerator, period is in the denominator. If one of them gets smaller, the other one has to get smaller too in order to keep everything constant. So you actually saw that when I demonstrated the apparatus. When I sped up the platter, that would make my period of rotation smaller, and that also caused the radius of rotation to become smaller too.